Hello y'all, welcome to lesson 4 where we will be making predictions from tables and graphs. Our learning target is that you should be able to use your knowledge of a linear function and your intercepts to make predictions about situations. Let's dig in. I'm going to give you a couple options with these. If you look over all these questions and you look at this graph and these tables and you feel like you totally understand how to answer all of this with the knowledge you already have, feel free to just treat these notes as another journal problems. You can skip the video and just do them. However, I will be checking to make sure that these are thorough and correct. So if you look over this and you're unsure about some of them, go ahead and stick around and watch. I'm going to answer all of these and talk our way through how to find these answers from graphs and tables. Alrighty, so this graph right here represents two cars traveling. We have car A and car B. Our x-axis is being represented as time in hours, and our y-axis is being represented in distance as miles. And let's go ahead and mark car A and car B. So car A will be our green car, and car B will be our red car. All right, let's dig in. First question we are being asked is which car is traveling faster and how do we know? Let's start answering that by looking for rate of change, and let's start with car A. All right, since we know we're working with miles and hours, we're going to be looking for a rate in miles per hour. And what we can look for at car A is we have this line where we can see that in 1 hour, 2 hours, this car was right here at 80 miles. So we could start by just writing that down. And we can make some more sense of this. I'm going to erase all that by looking at, well, if it went 80 miles in 2 hours, that means that it went 40 miles in 1 hour. And if you look at where this is, car A is at the 1 hour mark, it's about halfway to 80. So we would assume then, well, we don't have to assume because we just did the calculation, that this would be 40 right there. Okay, so now we have that rate. Let's go ahead and write it down. And then we can look at car B. Okay, so we're going to use the same system and say, well, in this case, since it's started traveling right here, that means that this is actually only 1 hour. And in 1 hour, this car made it to 80. So we already have our unit right there. And the only thing that confuses some people in the past is just seeing that even though the point right here is 280, because car B did not start at the origin, did not start at 0 like car A did, it started right here, that they reached that point 280 in just 1 hour. Okay, so car B is faster, it's twice as fast. All right, our next question, the lines cross at the point 280. What does this point represent? Let's get that cleaned up and add that point. So this is, again, the point 280. And what this represents is the place where the cars were at the same location. So at this very point, they are both at the marker 80 miles. And I like to think of this scenario as like two different cars going on a road trip, and maybe they're going to the same place. So I like to think of this as like maybe a rest stop or restaurant where they stopped and had lunch, even though they're driving. Maybe one's taking like a fancy scenic highway, so they're going a little bit slower, and one's taking the like fast interstate, so they're going a little bit faster. But anyway, that point is where they stopped and they met up. Okay, so what are the x-intercepts for these two cars and what do they represent about the situation? So starting with car A, our x-intercept is right here, and car B, our x-intercept is right here. Because again, this is your x-axis and your x-intercept is where those meet. So our x-intercepts would be 0, 0 for A, and 1, 0 for B. And since this is when y is 0, this means this is when no distance has been covered. And if we're going to stick with that road trip analogy, you can be like, maybe this is the point when both cars like got on their respective roads. So different roads, but they got on at the same time, perhaps? I don't know. Okay, only one car has a visible y-intercept. which is it and what does it represent? So again, our y-intercept is going to be where the line crosses the y-axis, and the car that actually crosses the y-axis is your A. And I'm going to erase this a little bit just so I can extend my axes. We can imagine that these axes go on, and therefore our lines would go on. But the visible intercept, so car A intercepts at the origin. And since that's where x equals 0, you can imagine that that is when no time has passed, or it's their starting point. It's the time they started. Then we're being asked to predict what the y-intercept would be for then car B and explain our thinking. And so since we know these rates of change, and we know that in 1 hour, this car is traveling 80 miles per hour, we can look at what is happening in this space right here along our x-axis. And what happened there is that if we kind of work backwards, that is 1 hour. So to go from this point to where x is 0 is 1 hour. And if they're going 80 miles an hour, working backwards, if this is -1, then this would be -80. So if you go back in time 1 hour, then you would see go back in distance 80 miles. So this would be the point 0, -80. And what that would represent to me, if using the same analogy, like maybe this car had to go run errands, or maybe they were in another town and they needed to like catch up before they officially started the road trip. Does that make sense? If not, come talk to me about it. I'm happy to clear it up. So I'm just going to write down that since the rate of change is 80 over 1, or 80 miles in 1 hour, that could also mean that 1 hour ago they were 80 miles away. So again, that whole concept of negative time being ago, and in this case, negative distance being 80 miles away from that starting point. All right, let's check out some tables. Okay, so we're going to use the same graph, and we're just going to fill in information we already know, and then use the skills we used in the last class to kind of fill in the rest of this data. So put in what we know. Let's start with car A. We know that car A, when x was 0, y was also 0. And we know that for car A, when x is 1, we had already done that calculation, that when x is 1, it's about right here, which we said was 40. And we know that in 2 hours, they were at 80. And so then using our reasoning from the last class, if x increases by 1, and y increases by 40, that means that our rate of change is a change in y over change in x, so that is a change of 40 over 1. So we can fill in the rest of this. So we've got 120, and then throw 40 more on there, and we're at 160. Whoops, there we go. Okay, so car A, there's that rate of change, and that y-intercept once again so car A, the y-intercept is 0, 0, and this would be in 0 hours, they had gone 0 distance. And just for giggles, that represents a proportional relationship. So car A is proportional because it crosses through the origin and it's linear. Okay, let's do car B next. So what we know about car B is we remember from that last slide that at 0, it was at -80. When x was 0, y was at -80. And then at 1 hour, it's at 0. So there's that 1 hour right there. And in 2 hours, it's at 80. So then we can use this and say, well, when x is increasing by 1, y is increasing by 80, and that checks out with our rate of 80 miles per hour. So then we can just add 80 here. So we have 160, and then add 80 here to 240. All right, so added 80 there. And so for B, our change in y over change in x is 80 as y, or I should say as x increases by 1, y increases by 80. And so our y-intercept here, again, y-intercept is where x is 0. So for B, our y-intercept is that point 0, negative 80. And that means that in 0 hours, this car was 80 miles behind the other car. I need to move my slide up a little bit and get some more space there. So in 0 miles, car B was 80 miles behind car A. So this is what you're going to be doing for your journal problems and your proficiency checks. You're going to be looking at a rate of change in a graph and a table and answering some questions about situations. If you have any questions or you'd like any support, oh, there was Bella saying hello. Go ahead and hit me up. I'm happy to help always.